We've been talking about galvanic cells, and remember that again, galvanic cells basically have two parts. We have our anode part and our cathode part, and different sort of redox parts occur at those sections of the galvanic cell. In the anode section is where we have oxidation occurring, basically giving off those electrons, and it goes to the cathode side of the cell where they accept those electrons, and it's where we have reduction occurring. We saw a couple of things that we can use our SRP values to help us determine sort of which one is the anode and cathode when we are not given any piece of information about what's going on. If we're given a piece of information, we obviously should use sort of what's going on in the reaction or whatever we are given to figure out what's being oxidized and what's being reduced. We then sort of tied these guys into a couple of sort of thermodynamic sort of relationships that we've seen before, and also equilibrium constant. We saw that we could tie our E of the cell, which again, we talked about a number of times at this point. You could do it one of two ways, but we'll just go with E of the cell is E of the cathode minus E of the anode. Remember, if you're using the subtraction here, we are not going to change the sign that we find in the table. If you decide to change the sign, then you should add these guys together instead of obviously subtracting them. We saw that the delta G is equal to minus NFE of the cell. And this is sort of a relationship between E of the cell and delta G. And the relationship that we see is a positive E will result in a negative delta G, meaning, again, the reaction should be spontaneous, should be heading to the products. And if we end up with a negative E, that negative and this negative here, again, will turn our delta G into sort of a positive value, being non-spontaneous, which means it will probably stay on the reactant side and not so much head to the product side. F is Faraday's constant, which is a constant, and 96,500, and N is the number of moles of electrons that are being transferred. Remember, when we talked about N, it is the total number of electrons that basically went over, from the anode to the cathode side. Again, you don't want to add up the electrons in each half reaction. For example, if you have 3 in one and 3 in the other, the N value would be 3, it wouldn't be 6. So you don't want to add those guys together. We also related this to the equilibrium constant. We saw that basically E of the cell is equal to RT NF natural log of K. This is our cathode minus anode. R is our gas constant, which is more the energy one. RT is our temperature in Kelvin. And again, is still our moles of electrons. And F again is our Faraday's constant, which is our 96,500. This is obviously our equilibrium constant. And sort of the relationship that we see here is one that we sort of would expect, kind of looking at all these relationships. They all really do sort of tie together when you're maybe calculating the equilibrium constant. Like normal, if we have a sort of large value of K, so K is greater than 1, that means obviously we have more products at equilibrium, which means we would expect our E of the cell to be a positive number, and that would obviously expect us to have a delta G that's negative, and vice versa. Again, they really do work together. If our K is less than 1 or a small number, we would expect us to probably have a negative E of the cell and a positive delta G. So those sort of relationships sort of go together. Any questions on any of that there? And that's what we saw, I think, on the last example that we sort of went through. We had a negative E value for that particular one we just did previous to this slide, and we ended up with a very small value of K, which again does make sense in that sense. So what we're going to talk about now is sort of the effect on concentration within sort of galvanic cells. So normally we, a lot of times it seems sort of standard conditions. And a reminder, when we sort of talk about standard conditions, kind of normal table type conditions, When we're dealing with molarity, that's 1 molar. We're doing something with pressure, that's 1 atmosphere. Usually temperature is about 25 degrees Celsius. So, if we change any of these sort of conditions, it does have an effect sort of on, the cell voltage that you may get, um, and other sort of values as well. So let's take a look at sort of what equation we get there when we are under sort of non-standard conditions. So let's take a look at each of these guys here. So these are some of the equations obviously we've seen up to this point. That's our delta G equation from the thermodynamics chapter. That's our pretty much delta G that we saw here. Since both of those are delta G, we can set them equal to each other. And when we do, we can do a little bit of rearranging. And we end up getting this equation here, which is essentially the Nearst equation. And the Nearst equation, you could kind of think about it in the sense of it is sort of under non-standard conditions. So what that means is basically something like we just talked about there is not sort of standard. So the concentrations, which is very common, is maybe not 1 molar for everybody. So if you don't have 1 molar for concentrations for everybody, you do need to kind of look at the Nearst equation here and use it. Again, if you're dealing with something that has pressure, that as well, that's not 1 atmosphere, you should kind of look at the Nearst equation. So what are sort of these values? Kind of like the delta G one that we saw in the thermodynamics chapter. This is sort of like the non-standard conditions, right? And this is the standard conditions, textbook table type conditions. Same sort of thing here. So this E is sort of under, if you want to think about it, kind of those non-standard conditions. Again, something is not 1 molar or 1 atmosphere or something of that nature. This is our normal E of the cell. So that is our E of the cell, which is our cathode minus our anode. The rest of these guys are sort of our normal guys. This is our R, which is our gas constant, that 8.314 version. We got our T, which is our temperature in Kelvin, our N, which is our moles of our electrons, and again, our Faraday's constant there, which is our 96,500 joules per volt per mole. And Q is the same Q that we've seen previously in a number of chapters, including here. Q is our reaction quotient, which is, again, our products divided by our reactants. Again, calculated just like K, and make sure, obviously, if you have any type of exponents or coefficients, that you do put those in as well. So this is where we can basically figure out, what the cell voltage would be, again, if something was not so perfect in sort of their conditions. We also see a couple of equations, just like we saw previously with the other equation that we looked at, where at 25 degrees Celsius, which is this basically, which is what a lot of things are done at, a lot of these guys become constants, and we kind of reduce down that equation to one of these versions here. Again, just like previously, if you don't want to remember those two equations, you don't have to. Even at 25 degrees, you could just throw everything into the top equation here, and you will basically obviously get the same answer and stuff like that. So again, in case you want to use the reduced version of it, that's what those guys are. But again, you could always just plug the numbers in. I think I may have mentioned it before. Pretty much the only difference is, between these sort of three equations is with rounding, you'll sometimes get a slightly different front number, but the exponent part will be sort of correct or the same. And it just has to do with the log, natural log, and some rounding. But again, probably easier just to go with this one equation, put it in even at 25 degrees, and just put in pretty much all the numbers. By the way, this Nearst equation is pretty much where we got the previous equation that we just saw on the last page, because at equilibrium, when we're dealing with the equilibrium constant, E would equal 0, and Q would obviously become the equilibrium constant. So if you put those values into the Nearst equation, which is a good way you could maybe also think about how to get the other equation. And you basically solve for E of the cell, bringing that whole thing over. You get that equation that we just looked at the previous page there, the natural log of K. So you could also derive the previous equation from the Nearst equation as well. So, you can kind of get some of those other equations from there as well. Understanding that E is equal to 0 at equilibrium, obviously Q is equal to K. So that's sort of how they tied together. Any questions on that there? All right, so why don't we look at one here and sort of see what we got going. In this particular, will this reaction occur spontaneously at 25 degrees given this reaction? And you probably will need some values here. Let me get you some values perhaps. Let's go with, if you look up in the SRP table, the iron 2 to iron would be minus 0.44 volts, and the cadmium would be minus 0.4 volts. All right, so why don't you take a few minutes here, see what you come up with. We want to know again, will this guy be spontaneous under these conditions? See how we're doing. So first off, we are wondering if it's going to occur spontaneously. We have a number of sort of choices, but a couple of things that we should be able to recognize in this sort of situation is when we look at the concentrations here of these guys. They are not 1 molar, which tells us we're sort of under the non-standard conditions, which tells us that we do want to use really the Nearst equation that we just saw, which would be E is equal to E naught minus RT NF, natural log Q. Also very commonly messed up by people is this part right here. Sometimes people like to add there instead of subtract, so you want to make sure that you are subtracting in this particular case. So we do need to find a couple of things, including E of the cell. We need to find N, which is the number of moles of electrons. We also need to find Q as well. So first off, if we look at what's going on here, we do have an equation, so we do want to look at it. So we see that iron is going from +2 to 0 in this case. So iron is being reduced. Again, if you remember our number line there, going from +2 to 0, heading in that direction, which is the reduction direction. If we look at cadmium, it is going from 0 to +2, again, 0 to +2, heading in that more positive direction, going through oxidation. This again is opposite of what we see when we look at our SRP values. Our SRP values show that cadmium is kind of more positive out of the two, but in this case, cadmium's actually the one that is going through oxidation. Any questions on that there? So it's really important to remember, as we talked about, that you do want to make sure that you really do look at the equation if they give it to you, or if they give you some information in words, that you follow what they say about it in words. We could also see, just looking at our 2 half reactions from our SRP table, we see that the value of N here will equal 2. Again, cadmium giving up 2 electrons, iron in this case picking up 2 electrons, and again, the value of N is 2, not 4, so we don't add those numbers together. What else do we need there is Q in this case. So Q is going to be our products over our reactants, which in this case is the cadmium ion divided by the iron ion. These guys being solid like normal will not be included in our Q expression. Also why we're only given 2 concentrations, right? So that works. All right, so we'll start with E of the cell here. So E of the cell going to be our E of our cathode minus our E of our anode. Again, here, since I am subtracting, I am not going to change, or not going to add them. I'm not going to, because that's what the subtraction is there for. So our cathode, we decided, was our iron, which would mean that we're going to take minus 0.44 volts minus, again, because I'm not going to change the sign, minus 0.4 volts. That will change the sign for me. Gets me a minus 0.04 volts. Any questions on that so far? So under sort of standard conditions, we can make the assumption that this cell is non-spontaneous under those sort of standard conditions. So what we're looking at now is, since we're not under standard conditions, we really kind of played with the concentrations. Will this reaction perhaps become spontaneous? So to do that, we would now go into our Nearst equation. We're just going to plug in everything we got going on, the numbers, 0.04 volts. That would be minus our R, which is our 8.314 joules per Kelvin per mole. Our T it was, right? And our T is 25 degrees, which if we add 273 to it becomes 298 Kelvin, divided by our 2 moles of electrons and our Faraday's constant, times the natural log, again, of our cadmium over our iron. So our cadmium's concentration was 0.01 and our iron was 0.60. Any questions on that there? All right, so again, do some cleaning up of some of this here to see what we got to work with. So we'll start with just the 0.0, actually we'll start with the 8.314 times the 298 divided by the 96,500, and now dividing that by 2, which, by the way, if you do just that division part, that's where you get that 0.0257 number we saw earlier. And we end up with minus 0.04 volts minus 0.012837. I'll take it to a few digits. We'll also divide out the 0.01 divided by 0.6, gives us 0.0166667. We'll do some rounding. Again, kind of cleaning it up one more time here. We're going to clean up this part of it. So we're going to take the natural log of that number. We're also going to times it by 0.012837. Going to get us that minus 0.04 volts minus a minus 0.05256. At this point, we could then add both of those numbers together. So or subtract, I guess, both of those numbers. Minus 0.04 minus that number there. Going to get us a voltage of 0.013 volts in this particular case. Any questions on any of those sort of steps? So what does this mean? Well, this means that under these conditions, unlike under sort of standard conditions where this cell was non-spontaneous, under these conditions here, this reaction would be spontaneous. Here we got a positive E, which would imply our delta G would also be negative in this case, also imply that our K value would be, above 1-ish, or on the larger side. Not a giant voltage, but definitely we were able to kind of turn it from a negative cell voltage into a positive cell voltage. Again, here by really sort of manipulating the concentrations of everybody and allowing really this redox reaction to sort of become more spontaneous. Any questions on any part of that there?
I have a quick question about the reduction half reaction.
Yeah.
So how did it get to Fe at the end as a product?
Let's see here. It's a good question, and the answer is I think it's just an extra 2 that the publisher put in there. To be honest with you, so let's see here. Iron 2, they're both 2. Yeah, the 2 actually shouldn't be there. Thank you.
Okay, I was confused. Okay,
Yeah.
thank you.
I think it just got thrown in for free. Other questions on that? Okay, so yeah, so obviously that 2 wasn't there. I mean, multiply or added those 2 half reactions together, you would end up with cadmium, which is what we have here. We have the iron 2, and then we obviously have the iron with no coefficient, and then the 1 cadmium there. So yeah, so it's definitely should not be there. Other questions on that? Okay, then why don't we try another one here? For the following, balance the redox reaction here from the half reactions. Basically make sure all the electrons cancel and all that good stuff. And calculate E naught and the equilibrium constant here. So see what you come up with in this case. So we got several things here. We want to just kind of balance the 2 half reactions, kind of get the overall reaction. We also want to find the E of the cell. We also want to find the equilibrium constant. So first off, a couple of those things should tell us sort of what formulas we should use. Obviously, E of the cell would be our standard. E of the cell is our cathode minus our anode. Obviously, the one that we saw had the equilibrium constant in it would be that E of the cell there is equal to our RT NF natural log of K, as we just talked about, kind of from the Nearst equations where we sort of get this guy. So these are sort of the 2 equations that we're probably going to use here. We would not use the Nearst equation here because we have obviously no concentrations given to us. So we could probably safely assume that we're under standard conditions. We also don't have a temperature here given to us, but it's also pretty safe to assume that it's probably 25 degrees Celsius under sort of standard conditions. So first off, we do want to kind of figure out what is our anode and what is our cathode. So we do have our SRP values given to us down here. Looking at our SRP values, we do see that the S406 is more positive. So you may be wondering, you know, is that going to be your anode? Is that going to be your cathode? And is this one here going to be your anode or cathode? So remember, in this case, we cannot just simply go by these numbers because they did give us an overall reaction here. So we do want to look at the reaction and sort of see what is happening here. And when we look at the reaction, you can look at chromium, for example, here, which would be easy, perhaps. That's +2 to +3. That means that chromium is being oxidized. Right. By default, it would mean that this guy here is being reduced. You may be wondering, you know, what is sort of the oxidation states going on there? So there's a couple of ways you could kind of look at it. First off, you could do oxidation numbers. You actually get something like a 2.5 there for sulfur. And on this guy, you get like a 2. So it's going from plus 2.5 to +2, which is being reduced. You could also look at sort of the other definition of reduction that we talked about. Remember, reduction is gaining electrons, also losing oxygen as you go to the right. So sort of losing some oxygen here as we go to the right as well. So that's another definition. So in this particular case, it actually does sort of follow what we see here in terms of our SRP values. This guy is going to be our cathode. This guy here will then be our anode in this particular case. So that's what we need to really calculate E of the cell. But first off, we can do some of our balancing. A couple of things need to be done. First off, that means that this guy is the anode, which means really this reaction needs to be reversed. So if I reverse that reaction, I get a Cr2 plus that goes to a Cr3 plus and an electron. When I reverse that reaction, technically my E in my cell would then become plus 0.50 volts. In addition, I also have 1 electron in the top guy now and 2 in the bottom, which means I really need to multiply that half reaction by 2 to get the right number of electrons all the way across. Remember, when we multiply by 2, it has no effect on this value. So pretty much I'm just going to eliminate this guy out of it here. So now what we have is our reactions that we can add back together. And when we add those reactions back together, our electrons should cancel out like normal. So our electrons would cancel. That would leave us an overall balanced reaction of 2 chromiums plus an S4062 minus goes to a 2 chromiums with a +3 charge and a 2S2032 minus. That hopefully should be balanced. You got 4 sulfurs on each side. We got 6 oxygens on each side, 2 chromiums on each side. Overall charge there on the left is +4 and -2 is +2. Overall charge here on the right is +6 and -4, which is +2. So this would represent the balanced equation here that's happening. Any questions on that there? Now we pretty much can get to the calculation part here. So in this particular case, I actually did change the sign. So remember, I could just add these numbers together now. But since I already wrote that formula up here, I will stick with the original sign. So I'm going to take my cathode, which is 0.17 volts, minus my anode, which is, before I messed it up there, 0.5 volts. And again, it's going to change the sign. That's again why we could just add the numbers at this point, since I did change it. And that's essentially what we're doing. And we will end up with a cell voltage of 0.67 volts for this cell. Any questions on that? By doing our balanced half reactions and I crossed them out, we now see also that N is equal to 2. And that's pretty much what we need down here. So that would give us a 0.67 is equal to our R, which is 8.314. And our temperature of 298 divided by our N, which is 2 moles, and our Faraday's constant. And that's going to equal our natural log of K. So we're going to do some kind of cleaning up here on the right-hand side. So if we clean up all that stuff there, our 8.314, our times our 298, and divided by our 96,500, divided by 2, gets us a 0.67 volts is equal to 0.012837. By the way, unit-wise, Kelvin canceling, moles canceling, joules canceling as well. And we do end up with sort of just a voltage type of thing happening here when it gets divided. Doesn't really matter since we're solving for K. The units will pretty much cancel out anyways, because K has no units. So we're going to divide basically this to the other side. So we're going to take our 0.67 and divide it by our 0.012837. That is going to get us about 52.1922 is equal to the natural log of K. To get rid of the natural log of on each side, we're going to take the E of both sides. We're not going to insert any negative here because there is no negative, so don't insert that. Again, the natural log and the E will pretty much cancel out. That gives you K is equal to, in this case, I can hit the right number button there. Try that again. It looks like perhaps 4.6 times 10 to the 22. Again, unit-wise, there are no units since it is K as well. Any questions on any part of that calculation there? Does all these numbers sort of make sense? Well, let's see. We ended up with a positive cell voltage, which would imply that probably our delta G is going to be negative, which means reaction is spontaneous heading towards the products. Heading towards the products would imply that we should have more products than reactants at equilibrium. Also should imply a larger value for K. And I would say that's a pretty large value of K. So again, those things do make sense when you kind of put them all together. Any questions on that? Questions on how to use the Nearst equation, calculate K, calculate G for a galvanic cell. Okay, so the next thing we're going to talk about batteries here. You're not going to be responsible for any type of half reactions or anything like that. You just kind of need to know sort of the similarities to batteries and maybe some of the differences between, say, a battery and a traditional sort of galvanic cell that you would sort of build in a laboratory. So let's start talking about batteries here. Batteries are really a galvanic cell, or sometimes a series of galvanic cells, that it can be used as sort of a direct source of electrical current and a constant voltage. It is sort of like a galvanic cell if you think about it. You put your batteries in your battery compartment. Usually there's like a wire in there, right, where the batteries kind of sit against, and that's sort of the wire, kind of like in a sort of traditional galvanic cell, right, where you have, you know, your two sort of beakers sloshing around, and right, they're connected through sort of a wire giving your voltage. So, you know, that kind of wire you see in the battery compartment sort of acting just like sort of a wire that those electrons travel from sort of the anode side to the cathode side in these sort of redox reactions. Obviously, a couple of things that are major differences between, say, a battery and a traditional galvanic cell is if you try to put that probably in your battery compartment, that would not be good. Everything would be sloshing around, spilling out, and making a mess. So they're really just kind of self-contained. They also have other things in there that sort of act as the salt bridge. So they don't really have a salt bridge, a traditional sort of salt bridge, but they do sort of contain certain components that sort of act for that function or act as that function in it. But basically those electrons, you know, they go out, they do some work, and you know, they power your device, and they kind of come back and sort of complete this sort of circuit there, and gives out a constant voltage depending on sort of the size of battery that you sort of choose, or the type of battery that you choose. Now, also why, right, when you put your batteries in backwards in your device, things do not work so well. And that's because when you put your batteries correctly in, you got your flow of your anode to your cathode. When you technically put your batteries in backwards, right, you're kind of reversing everything, which means your anode becomes your cathode, cathode becomes your anode. And if normally it's a spontaneous process, when you put it in backwards, you're now making the opposite process occurring, the non-spontaneous process, basically, and getting kind of a negative cell voltage, if you will, because it's sort of running backwards. So when we look at batteries, there's different types of batteries, obviously, that we probably have seen, obviously, in your life. This one here, I'm assuming Duracell, perhaps, maybe. This is what is sometimes referred to as a dry cell. It's really a cell without a fluid compartment. It does have an anode side, which is the zinc container. So here's our zinc container over here. Our anode, where it's kind of negative, right? So like electrons would not want to be going there, right? And kind of be traveling around sort of that way. And it goes to sort of our cathode, which is this carbon rod that's sort of in the middle there of the battery. Inside, it's in strong contact with, or in contact with, a MnO2 and an electrolyte. So it has a paste of some electrolytes here. Electrolytes are guys that basically break apart, sort of produce ions. That charge of ions here, this sort of paste, if you will, sort of acting like a salt bridge, kind of making sure, again, we don't get too much of a buildup of positive or negative charge on one side or the other, as we talked about in a traditional galvanic cell, right? If we don't have that salt bridge there, we're going to get this really kind of buildup of sort of negative charges where we don't want it, and positive charges really sort of where we don't want it. It's going to stop really the flow of electrons from one place to the next. So that sort of paste, if you will, that strong electrolyte sort of acts as that function within a battery. This type of battery has a voltage of 1.5 volts, regardless sort of the size, if you will. If you put a double A, triple A, D batteries, C batteries, the only real difference is sort of the size, which means they could kind of go longer, right? So they have a lot more, obviously, material to keep the reaction kind of going longer before sort of the battery dies. If we look at sort of our anode reaction, it is our zinc going from 0 to +2 here, being oxidized, and obviously we have our reduction sort of happening over here with actually our MnO2 that's happening, and it's going from here +4 and over here. That's a lot of math in the morning, but we'll go with +3 and try that there. And it's getting reduced in this case. So overall, this is the reaction that's taking place. And again, it really is a basic sort of redox reaction, very similar to what we see in a traditional galvanic cell. Obviously, less mass, a little bit more transportable, obviously, as well. Again, you're not responsible for these half reactions or anything like that. I'm not going to ask you to write them and stuff. Another type of battery is one here, which is a mercury battery. And again, kind of similar in the sense it's used a lot in medicine, electronic devices, a little bit more expensive. It has a zinc sort of anode as well. Again, that's where our oxidation is going to occur in contact with a really strongly alkaline. Alkaline means basic electrolyte. And also mercury 2 oxide as well, which is again why it's called a mercury battery here. It also has, again, sort of a steel there as its cathode sort of site where reduction will occur. And the one thing that makes this battery sort of long lasting and stuff like that is there's really no change in the electrolyte composition during operation, which means, this center part, which again is sort of that part that helps everything keep flowing, acting kind of like the salt bridge, because there's not a big change occurring in sort of this part of it, is able to kind of go for a long period of time with very little sort of degradation or a breakdown and stuff like that. The other thing that really makes something really long lasting is when you look at sort of the overall reaction, you end up with a lot of solids in there. And a lot of solids implies that you're sort of regenerating the parts of the reaction that you need to kind of keep the reaction going. Also really important in terms of rechargeability of batteries and stuff like that. This one has a little bit lower of a voltage, which is a 1.35 volts. But again, we sort of see our same sort of oxidation occurring there. And then obviously here we have our mercury going from +2 to 0 here. And again, the main part here having that sort of solid being produced, really sort of critical in terms of allowing it to be a very long lasting sort of battery. A lead storage battery, which is commonly what is used in our cars, are basically a bunch of sort of cells together, about 6 of them. Each of them gives you about 2 volts for a 12 volts sort of charge there. When you turn your key, that's enough to sort of power the ignition circuit and other electrical sort of systems in your car, unless of course you're on those days when you're running really late and you turn it and it does not start. But it's enough to really kind of get things to click over and turn over these sort of batteries. It is sort of rechargeable, which is, again, reversing the normal sort of reaction. If you think about, how come the battery perhaps doesn't sort of just drain, we do have things like certain colors, alternators and stuff like that, that sort of alternates the current, so we do not sort of just kind of drain out the battery. Also, why, if you ever have had your car jumped, they tell you to let it run for a while before you shut it off to sort of recharge it a little bit, obviously, before you turn it right off and you're stuck again. We can sort of check the health of a battery by looking at its sort of density. In cold weather, sometimes electrolytes get a little bit more viscous in there, makes it a little bit harder to turn on. So sometimes if you live in really cold weather, sometimes it's troublesome to start your car. Here's sort of a cross section of our sort of car battery, or traditional sort of car battery. And we have our anode here, right, and our cathode. Speaking of jumping, you always wonder, well, which one should I put on which, right? Should I put the red or the black sort of lead on each of those? And sometimes now in a lot of cars, batteries are not even like actually in the engine anymore. They're sometimes like in the trunk or below the seat and stuff like that. And they just have sort of the kind of terminals in there that you could use to sort of jump. They kind of run the terminals in there for you to jump it in the actual engine. But the actual battery a lot of times nowadays are, you know, sort of in the back of your car and not even actually in the engine in a lot of cases. But we do see, again, sort of this series of cells. And by putting obviously a series of cells, you could gain a lot more voltage by doing that, running it in a series. We have like a very strong electrolyte like sulfuric acid in here, which is our battery acid. Obviously very strong electrolyte, going to break apart a lot of ions, again, allowing all this sort of redox reaction to continue to occur efficiently without sort of breaking down. Here we see our lead going from 0 to plus a 2. And on the other side there, we do have our sort of reduction taking place when we look actually at the, excuse me, if we look at the, what we got here, the, I'm getting old. Our sort of hydrogen sort of taking place over here. So that's lead 2, and that's this is lead 4 here, and that is lead 2. And over there is our reduction that's taking place between there. Another type of battery is one that is a lithium battery. And lithium batteries, we have an anode which actually has a conducting carbon sort of species like graphite with little holes in it. And we have our lithium that's basically going from lithium with no charge to lithium with a +1 charge, kind of migrating through this electrolyte solution to the other side, where we have reduction occurring with some type of transition metal that can hold those kind of lithium ions that are going. The nice thing about this is lithium can be sort of recharged hundreds and hundreds of times without much deterioration of sort of the products. And again, recharging it will sort of bring the sort of starting material back by applying that external electrical current and kind of regenerating your starting material that you need. Also, it's a relatively sort of light material, which is why sometimes they're used, right, in lithium batteries for whatever electronic devices, power tools, you know, those type of things as well. A fuel cell, which is, you know, not a traditional battery, sort of operates a little bit like a battery. In a traditional sort of fuel cell, we kind of, this is a hydrogen fuel cell. Here we would sort of insert a flow of hydrogen and oxygen. And this is sort of what originally, years ago, they were trying to kind of turn cars into sort of this hydrogen sort of fuel cell. The reason they wanted to do that was this is pretty much what would come out of the tailpipe, if it had a tailpipe there, would be basically water. So you wouldn't have much of pollutants sort of happening. We're obviously not a hydrogen economy, so we've now moved more towards obviously hybrids and now straight electric sort of battery sort of cars and stuff like that. But you basically feed in your hydrogen and your oxygen, hydrogen being your anode going from 0 to +1 being oxidized, oxygen going from 0 to -2 here, being reduced and getting electrons. And again, the benefit of this is, you know, you sort of get just water out of it. Any questions on batteries? So again, you just need to know sort of general idea what batteries are, how they're similar and a little bit different from your traditional galvanic cells. Again, you're not responsible for any of the sort of half reactions or anything like that. Any questions on that? Okay, we're also going to talk about corrosion and sort of, you know, how it relates to electrochemistry and sort of galvanic cells and why we see certain things. So corrosion really is sort of returning their metals to their natural state. It's really when metals go through oxidation is pretty much what we consider sort of corrosion. About 1/5 of the steel is pretty much made to replace, metals that get rusted. Pretty much all metals that have an SRP value less positive than oxygen is susceptible to going through corrosion. So why is that? Well, if we think about our SRP values and we have oxygen being more positive than a metal, that would mean the metal's SRP value would be more negative. And what do we know about SRP values? The one that's more positive would be our cathode. The one that's more negative would be our anode, which means in this sort of arrangement, the oxygen would be our cathode. The metal would end up being our anode in that arrangement. And that means that the metal is going to lose those electrons and pretty much become oxidized and go through corrosion, basically. So as it goes through that oxidation sort of process, just naturally it's going to be a spontaneous reaction that's going to occur. So just by obviously being in oxygen, being in the air, that reaction is going to just kind of spontaneously happen. And we would expect those metals to kind of go through, obviously, corrosion or oxidation. When we get a positive E value with the reverse for a metal, they combine. And again, that's going to be basically a spontaneous process. So does this corrosion that occurs sometimes spontaneously with metals, is it always a bad thing? And the answer is not necessarily is it always a bad thing. Sometimes when metals actually go through corrosion, they actually end up creating a layer of protection. So some metals, when they kind of go through corrosion, they end up making this sort of layer of corrosion, if you will. But this layer on top, if it kind of hangs on there, actually will protect the metal that's below, right? So further metal from going through sort of that oxidation or corrosion process. So not always is it a bad thing necessarily that, corrosion occurs. It can make a sort of layer that actually does protect. For example, aluminum. Aluminum will form basically aluminum oxide, which this sort of layer will then sort of protect the metal that's underneath it from going through further sort of corrosion. So not always necessarily a bad thing, but we oftentimes think about sort of corrosion of metals as a bad thing. And it's really because of, pretty much iron. When we think about iron going through sort of corrosion and this oxidation process, it also forms a layer when it kind of goes through this corrosion. So it forms this layer of protection, but it's really not a layer of protection in the case of iron because it's basically rust. And as you've ever seen anything that's rusted out, it's because this rust basically will fall off. And once it falls off that layer, now new metal can be further corroded, which will create a layer that will fall off. And then, before you know it, you create a layer that falls off. Before you know it, there's not much metal left as this sort of process continues, keep forming that layer. Then you have a very small piece of metal that's left as you almost kind of punch your right through because there's pretty much nothing left. So in the case of iron, and why, a lot of times we think about sort of corrosion as being always a bad thing, we do sort of see that aspect of it occurring, and obviously that creates a lot of problems. Copper sometimes forms obviously a greenish carbonate or that patina color, which people like, right? So that's kind of a good one as well. Silver is tarnished by silver sulfide that's happening. Now gold is much larger than O2, so we don't get any appreciable sort of corrosion of gold in air. So what happens when gold hooks up with basically oxygen? So when we have gold and O2, in this case, gold actually has a much larger SRP value, or a much more positive SRP value than oxygen. So when they actually get together, the gold actually becomes the cathode and the oxygen actually becomes the anode. So all the oxidation and bad stuff that occurs actually occurs over here, leaving our gold metal pretty much okay and not really going through any significant amount of corrosion sort of spontaneously in a natural sort of process. Any questions on that there? So we kind of talked about it just a second ago, but what do you need for sort of rust to form? you basically need a few things. You basically need iron, you need some oxygen, which you get in air, and you need a little bit of moisture. And those are really your good sort of things that you need for basically rust to form. It actually occurs in a couple of steps. Iron goes from sort of solid iron to iron 2, and those electrons sort of travel through the steel to the cathode side, uh, which is basically the oxygen. And then actually the iron 2 will then sort of go through further oxidation to iron 3 and make pretty much rust, which is iron 3 oxide. So actually iron gets sort of oxidized twice in that sort of process, if you want to sort of think about it. Here's sort of a picture of that. Again, our iron 2 iron getting oxidized to iron 2, sending those electrons over to the oxygen. With that moisture there, the iron 2 then gets sort of oxidized as well to the iron 3, kind of traveling over and combining with the oxygen coming in, and that's where we get our rust that's basically forming in this particular case. Again, kind of making water. Water also will have the oxygen or oxide involved in there, and we will be able to sort of form that iron 3 oxide. Obviously, there's a lot of parts on sort of steel where these kind of non-uniform parts where it allows this reaction really to take place really nice, allows moisture and stuff like that basically to sit in those areas and allow this reaction to occur relatively easily. Obviously, this sort of layer that forms, which is rust, as we talked about before, sort of the problem is it can fall off pretty easily, again exposing new metal underneath to kind of further and further sort of corrosion occurring, resulting in a lot of money sometimes to replace certain things that have basically been sort of corroded out or gone through corrosion. How do we sort of protect against corrosion? There are some ways that we can prevent corrosion, and here are some things that we could kind of do along the way. We can apply some type of paint or metal plating, right? There's Rust-Oleum paint, hence the name Rust-Oleum, probably should prevent rusting. You could also do some type of plating of your steel with chromium or tin. They form an oxide. The difference is with that coating that is formed pretty much will stay on there. It won't fall off and stuff like that. You could also do some type of galvanizing with zinc. It's basically a mixed oxide with a carbonate type of coating. Zinc is more active metal than iron. So what that means, if we look at the SRP values here between iron and zinc, we see that between the two here, iron is actually going to be more positive between iron and zinc. So iron will be more positive, zinc will be more negative, which means when this redox reaction occurs, our iron is actually going to be more of the cathode situation. Our zinc is going to be really in the more anode situation with oxygen. And this is where all of the sort of oxidation and corrosion is going to occur, thus protecting the iron that's underneath it. So it's sort of like a sacrificial sort of coating. It creates pretty much the redox reaction happening, on that surface. And again, it's going to have all the oxidation occurring here, pretty much protecting the metal that's underneath of it. We can also do things like alloying to prevent corrosion. We basically sort of add some other metals in there, and it essentially will change the sort of SRP value of that metal to more of a noble metal, which means it's probably going to have a SRP value kind of greater than, more positive than oxygen, which is going to prevent the corrosion process to occur kind of like gold does sort of naturally. Another couple of ways we could kind of protect is through a cathodic protection. So for example, if we take something like magnesium that's connected by a wire to a tank, like an iron tank or some type of storage tank that you would maybe bury underneath the ground to store things. Magnesium is a better reducing agent than iron. So what does that mean? Well, remember, things that are reducing agents are the things that get oxidized. So here, the magnesium being a better reducing agent than the iron means that when we sort of hook that wire up that has the magnesium on it, all the oxidation is going to occur over there at the magnesium site, not going to occur at the iron site. And that's really good if that's your tank that's buried under the ground, so it doesn't start to corrode and obviously spill out whatever's inside there. So again, that oxidation occurs as sort of the sacrificial guy over there at the magnesium, keeping, again, your tank pretty much okay. Sometimes titanium is used in ships. Again, it does sort of do the same thing. It sort of acts as a sort of sacrificial place where oxidation can occur, really protecting the metal in the ships from obviously going through a lot of corrosion in the air and the salt and all that kind of stuff. So here's sort of that situation if you bury sort of the tank underneath here. Again, with this magnesium present and sort of connected, this is pretty much where all the oxidation will occur. Again, keeping your tank in a good situation, not going to hopefully go through corrosion and start leaking anything out of it. So it's able to obviously prevent that. So any questions about corrosion? So corrosion, again, basically is the oxidation of metals that go through oxidation sort of spontaneously. In certain cases, it can be a bad thing. So you need to know sort of what it is, how it's prevented, a couple ways to prevent it, and stuff like that. Any questions on that? The last thing we're going to talk about here in this chapter is electrolysis. And electrolysis is the process where we basically use electrical energy to cause a non-spontaneous process basically to occur. So, we can cause certain things to occur that normally does not happen. So for example, if we had sodium chloride, under normal conditions, we do not see it breaking back into sodium metal and chlorine gas like as natural sort of components, right? You could heat up like your fries that have salt on it and you don't get back sodium metal or chlorine gas. You heat up the salt in salt water, you don't get that back and stuff like that. So it's not really a spontaneous process that occurs, but we can apply an electrical current to cause this to occur. And this would be obviously a chemical change, right, when we do this. So if we put this into a system such as this, some sodium chloride goes in, chlorine gas comes out, and basically molten or liquid sort of sodium leading to sort of solid sodium in that case kind of comes out. Now, when we do electrolysis, it is sort of opposite perhaps of what you might think the reactions are going to be. And what I mean by that is if we take something like sodium chloride, basically sodium chloride is a sodium ion and a chloride ion. And if we throw it through electrolysis, they're going to kind of become their natural sort of states, if you will. So the sodium and chlorine, which is a gas. So when we look at what's happening here with the sodium, it's actually going from +1 to 0, which means if we look at our number line here, it's going from +1 to 0. It's actually being reduced. While the chloride is going from -1 to 0 here, it's going from -1 to 0 in that direction. It is being oxidized. And that's why when we look at here our electrolysis cell, the oxidation half reaction is actually the chlorine losing a couple of electrons, while our reduction half reaction is actually the sodium doing that. And that's opposite of how it happens when we form it, right? When we form something like sodium chloride, we end up, and I'll just kind of spread those guys out. So sodium's going from 0 to +1, losing electrons, being oxidized. And the chlorine is going from 0 to -1, gaining electrons, being reduced. So again, we're sort of reversing this reaction, which means that these guys end up being reversed as well in terms of what is happening. So sometimes people get confused as to sort of, what the reactions would be in this case. We could let this guy run for a while. We could collect a certain amount of sodium. We get a certain amount of chlorine gas. That's basically happening here. So this is basically sort of a reverse reaction of sort of putting it together. Any questions on that? So, whoops, water is obviously another one that under normal conditions, right? We don't take water here and then see it break apart into hydrogen gas and oxygen gas, right? We don't typically see that occur, but we can, do an electrolysis sort of reaction here, run an electrical current through it. And really, you could even see this occur very simply. It's an experiment sometimes schools will do. You take like a 9-volt battery, hook it up to a couple of electrodes, put some water in there, and you could actually do this experiment relatively easy. Um, so this is what's happening here. Remember that we are sort of going backwards in this sense. And basically what's happening is we're taking our H plus to H2 and our O2 minus to our oxygen. So we're going from +1 to 0, again being reduced, going from really -2 to 0, being oxidized in this case. So that's what we see here. We basically have our water, where in here the oxygen is -2, going to 0, as I just put up there. And on our reduction side, we have our +1 going to 0 over here in terms of the hydrogen gas. Now, when we deal with water going through electrolysis, sometimes in problems, they really won't necessarily say it's electrolysis of water. They will mention something like this, like you did it in a dilute hydrochloric acid solution or some type of acidic water or something like that. And that's how you know that the sulfuric acid there is added really to sort of beef up the H plus concentration in here and allow this reaction to be more efficient as it's doing that. So sometimes when you do this electrolysis of water, sometimes you'll see this is sometimes written as sort of in like a laboratory, for example, it's like acidic water or something like that, where they've added some acid to it, again, just to sort of build up the H plus concentration and allow this to run more fluidly. We also see a couple of things as well. When you look at the test tubes there in the picture, that is the collection of the gas, and the gas is being collected in this empty space here, right? This empty space is really not empty. It has hydrogen gas and oxygen gas. Basically, these test tubes are filled with water. So as the water is being broken down into hydrogen gas and oxygen gas, they're being fed into these test tubes. The water that was in there originally is coming out. The gas is coming in. You can see the bubbles that are happening. You also see something that we should expect as well. We see that in terms of the hydrogen gas, there's like twice as much being collected as the oxygen gas. And that is because of the formula, right? It's H2O. So twice the oxygen to one of the, twice the hydrogen to one of the oxygen. And you actually do collect it sort of in that ratio as well. Any questions on that? So these are definitely the half reactions that you would use if you're doing some type of electrolysis of water, which is sometimes helpful to know. So let's talk about sort of the electrolysis here and sort of how we do these calculations. And there's sort of two sort of versions of this calculations. There's two pathways that are taken when we do these type of calculations. And basically we are given the current in amps and usually the time. So they'll tell you, hey, this is how long you ran this cell for, this electrolysis cell. The current, or a coulomb, or the charge, is equal to an amp times a second. So an important relationship when you're doing these calculations is that an amperage is equal to a coulomb divided by a second. And why that's important is it will also tell you basically the time that you ran it for. Maybe they'll tell you to in hours or minutes. If it's in hours or minutes, you do want to make sure that you do get your time into seconds, because pretty much the first part of this calculation is to take the amperage that you ran the cell for, which is coulombs per second, and you want to times it by how long you ran the cell for. The seconds will cancel, and you'll end up with coulombs at that point. And that is what it means here. You'll end up with basically the charge in coulombs. Is at this point that we use a number that we've seen previously, which is Faraday's constant, as a conversion factor. which we would use that there are 96,500 coulombs in a mole of electrons. That will cancel out the coulombs, and we will now have moles of electrons, which gives us to here. Now, what do we do sort of at that point? This is where the half reactions come into play. So for each of these sort of electrolysis sort of cells, as we just saw in the previous couple of slides, we have some half reactions. We have our reduction half reaction. We have our oxidation half reaction, where something is giving off. And basically what we could do is, I'll get rid of these for now. So we have our oxidation or reduction half reaction. We go to the half reactions and we find the moles of electrons to the moles of the sort of guy we're looking for, like the element we're looking for, maybe the metal, maybe the non-metal. And we come up with sort of a moles of the metal or moles of the non-metal to moles of electrons. And we use the moles of electrons here to do that. So we could do something like, hey, the moles of electrons from the half reaction, there's so many moles of electrons, give me moles of, say, a metal, for example. And that will then get us to moles of a metal, or again, could be moles of a non-metal as well. At this point, it depends on sort of what you're dealing with. If it's a metal, they may want grams. So if they want grams, then obviously you have moles. To get to grams, you use the molar mass, right, of the metal. Gets you to grams. You use the molar mass. But what about something like we saw actually in those two examples? One of them was like chlorine gas, right? The other one, which was the water, which was hydrogen gas and oxygen gas. So what sometimes happens is when we have a gas that we're dealing with, sometimes we're interested in the volume of that gas, which means a lot of times in these problems, you may need to go into PV equals nRT, the ideal gas law, and solve for volume. Volume would be nRT divided by P. The temperature and the pressure would be provided in the problem. And then obviously the mole, so what you got would be what you would be calculating for. And you could figure out, hey, I produce this much volume of this gas or that much volume of another gas. Any questions on that there? Okay. So